I appreciate this opportunity to speak to you about my experience with Destriero, but it's not a technical presentation. It has to do with how did we manage the program, and particularly the title, Partnerships and the New Management Approach. Why would that be of interest? And it's of interest because from the word go to initiate the Destriero project till the time that this vessel was completed, built, delivered, was only 25 months. At the beginning of the time go, all we had was a requirement and a blank piece of paper. So we're going to talk about how we managed to get there without falling off the edge of the earth, okay? This, I'm going to start off with, while I said this is not technical, it's about management, but I wanted to let you know right up front what was developed in 25 months. And the vessel shown during construction here in Italy, it was a 1,000-ton vessel, 67 meters, a little over 220 feet long. It had 52,000 horsepower in it, driving 3 Kamiwa water jets. The vessel was built out of welded aluminum and at the time that it was delivered in 1991, it was the largest welded aluminum vessel ever built. And the vessel was built in modules. The ship Destriero was built in 2 different shipyards, both owned by Fincantieri. One was in Riva Togrossa, and the other was in Muggiano, which was near La Spezia, where the modules were built, and it was finally assembled. And the owner of Destriero is Bravo Romeo Limited, which is an Irish company, okay?
Excuse me, sir. May I, and excuse my ignorance, but which of these specs are sort of extraordinary? Because I know not a lot about, so are any of these specs, or were they extraordinary for the time? Just trying to understand the whole.
There were a number of extraordinary things. One, like I said, it was the largest aluminum vessel ever, welded aluminum vessel ever built at that time. The water jets were the largest steering and reversing water jets that had been built at any time. It was the 3 GE LM1600 gas turbines. Only 4 were fabricated, and the rest were sold into the industrial market as to power remote pumps in pipelines. So there were we had 3 of the 4 gas turbines that went into of this model that went into the marine service. And also, I'll say, it's the fastest surface vessel. It's crossed the Atlantic unrefueled, which it did in 1992. It went from New York to England nonstop in 2.5 days, averaging 53 knots. Far faster than any other vessel like the SS United States. During this transit, it traveled over 1,400 miles in a 24-hour period and average 58, a little over 58 knots. So those are the sort of the extraordinary highlights.
I guess pretty much all of them.
Yeah, okay. And I don't mind interruptions if they're little questions, okay? And I get to decide what's little and what gets saved to another time. And here were the requirements that we were faced with, or I was invited to participate in. The design requirements, it was a two-phase program. Phase one was going to be build Destriero in its, you might say, its racing mode. And phase two was to complete the vessel as a personal family yacht, okay? And like I said, the requirements are 50 knots in Sea State 4 for 3,000 nautical miles without refueling. That's simple, and brief, but not necessarily as simple as I just said. And the other part of phase one was there should be no excessive accelerations or noise levels in manned spaces. In other words, ride quality had to be suitable for the family when it was finished as a yacht, and that the onboard facilities would be very, very quiet. And I was approached in early April of 1989 and asked if I would be interested in participating in this problem or this requirement. I said yes, and what, as much as anything, caught my eye is that I had already worked with gas turbine powered water jet propelled boats for the Navy and knew something about them, but I saw an opportunity for a lot of research and technological advances in a number of areas. And so as I said, yes, I was interested. I was retained to do a feasibility study. Are these requirements feasible in 1989? And I established with technical references that it was feasible. And that was delivered to the client on May the 1st. And this is what I delivered, is the dimensions of, may I just talk to this one? The waterline length in meters, the waterline beam in meters, and all of this area was a combination of dimensions that could meet these requirements. The difference is this blue region had the optimum drag or the minimum drag or hull, whereas while the ride quality was suitable up here, the drag was about 5% higher, but the potential of meeting the 50 knot average was within the capability of these geometries. Having agreed to join the team, and at this time there was not a design team or a design program. It was just, we got to the decision that we're going to do phase one. And so we're in the 1989 period, and there were a number of things that actually had to be done. We didn't even know if the shipyard would bid on such a job, okay? We didn't know if water jet suppliers or gear manufacturers or gas turbine companies would sell products to us. And so the first period of aggressive actions was in like from mid-May to maybe mid-June, where we were trying to identify shipyards that might build this or have the capability of build this thing that had yet to be designed. We looked at, and only at military shipyards in the United States and in Europe. And we made a short list. I sent out a request for interest. You know, would you be interested in a design build contract for this, or just build to our design? And in 7 days, we got 4 responses from 4 shipyards, 2 American, 2 European yards that expressed interest, and most of them even offered some very not well-defined suggested concepts of what the vessel might look like or what the size. They had not seen the feasibility area. And so we're getting to the point now that we believe we can find somebody to build it. And we begin to worry about how in the heck are we going to manage and educate the program. In other words, sometimes you bite on something that it might sting, you know, before you finish the job. And so with that point of view, we're getting to the starting point of the management program. I was one of people who came up with this requirement. And the principal that came up with the requirement, his attorney and I talked for a long day over how do we manage this animal. And there were things, you know, to really, you know, worry with. And these are the things that we discussed and talked about. Something like this had never been done before. So that implied right there that there's going to be some R&D involved in this time frame. The water jets and the gears and we're probably going to have to be custom designed for this project. There were 2 gas turbine suppliers that had products that could power this. One was Allison with the 571K gas turbines, and GE with their LM1600. These were new marinized turbines coming on the market. We knew that we had gotten some response that there were shipyards that might bid or participate in some way. And we discussed a long time, would this project be too complicated for a single manager? And we convinced ourselves that it was too complex for a single manager. As a matter of fact, we would probably be buying equipment and components from 6 or 7 different countries, among other things. Not much more even be considered are the, international laws of the sea, rules and regulations and things like that. And basically the investor, the attorney, and I saw this project as having technical risk. How is that? And it was technical risk with a very short duration. And at the end of this discussion, we came to an organized management choice of a 5-member management team, and each manager would have absolute authority over their parts of the responsibilities. And this is my cartoon of, as I see our management group working. The 5 managers, there was one was the requirements and financials, and I say, why was that a manager? There was a lot of financial activities, but the requirements was that to make this project happen, you couldn't have a lot of changes or any changes in requirements if at all possible. So the number 1 person was the God, the keeper of requirements sacred. And if there was some condition came up that absolutely we couldn't move ahead without a change in requirements, that person is the only one that could make that decision. The legal manager was responsible for looking for the financial conditions of the yards that might bid on this job. Would be the chief contract negotiator on contracts, and would be legal counsel to all of the managers if there were legal issues. Number 3 was design and R&D manager. That was me. That's the only person of this group you'll hear names for. I had, my responsibility was to get to a contract design package, and that's a long way from a blank piece of paper, and plan and contract for and execute research projects which included hydrodynamics, aerodynamics, and thermodynamics. And then number 4 was the contract manager, who would oversee and be in the contract facilities of the subcontractors. And then we had vessel operation, that after the vessel was finished and complete, his problem or responsibilities was to set up a company that would hire a crew that would drive the boat across the Atlantic, train the crew, provide the logistic support to get the vessel ready to run, like I said, train the crew, and take care of that, and also to look for sponsors to help support the cost of, the record challenge, the record run. And there were essentially, I'll go back, and on the bottom of this, there were 5 major contract groups. The propulsion machinery was owner-furnished material. There's a reason for that. There were separate contracts for water jets, custom co-dog gears, and gas turbines, and then another contract for the vessel construction, which included the responsibility to integrate all of the OFM that's going to be provided and the controls of all of those, integrate all the controls. The fifth contract group was the hydrodynamic and aerodynamic contracts that I had to plan and develop to get to a good design. So the reason for the OFM is in our early contacts with custom gear builders and water jet builders, the lead time on these projects after contract was generally running about 16 months for custom water jets, custom gears, and get the gas turbines packaged into some sort of a shipboard container that could be put in at the last minute. And the connections to the ship and the gas turbine work needed to be precise because the gas turbines were the last thing that went into the ship construction. And so that's why there was OFM, was because before we knew what the final vessel looked like, we had to start speccing out as best we could and hold open a couple of spaces, like what's the absolute gear ratio that we need on the gears and things like that. But that came pretty soon. So here is what the guidelines for the managers. Each manager had absolute authority for their responsibilities. And that means that anything in the design R&D side, I made all the decisions. You could get guidance from the others, but basically these 5 managers were sort of, you might think of them as a ring working together. They got together every 3 or 4 weeks, shared progress, problems, counseled each other, but only the manager that had absolute authority over his responsibility or their responsibilities was, so it made decision-making easier. There was not a committee. These 5 people, to go ahead, all you need was 1 vote, and that was your own vote, okay? And so this ring together, working together cooperatively, in essence was the boss, the program manager of this project. It was not a one person, and I'll repeat once again, there was no budget limit. And I know you can laugh about that, but you can't, I should say, it's very difficult to have a tight schedule and a limited budget. They don't work together. You can have one or the other. And also, this kept the decision-making of the individual responsibilities very close to the end product. You didn't have layers of decision-making. You in the government, sometimes you make a decision and it floats up to some other level of authority who can make a different decision, and going up that way. The decision stopped at these management of producers. We all kept in mind that the vessel had to be delivered complete in the water by mid-June in 1991. And this is the way the managers worked. And by the way, the managers, there were 3 Americans and 2 Europeans on this management team. And the meetings were held in English. They were held north of Charles de Gaulle Airport. That was an easy airport to get into and out of from any part of the world because we were often in many different places. We got together every 3 or 4 weeks, and you see the agenda. It was a constant, non-changing. Each manager reported on status relative to the schedule. Am I ahead of schedule? Ha ha. Am I on schedule or am I behind? And if they anticipated problems, they would bring those out. We would have discussions. We, the other 4 managers, could offer suggestions or ideas. But we had no influence on what the decider did, okay? And then when there was a problem, we did also discuss risk mitigating actions, which might be, can we get the requirements changed? Or do we add a new requirement? And to my knowledge, there were only 3 requirement changes in the whole program, and they were in the order of a specific example. In the contract build specification, there was a make and model number of a radio called out that was available at the time the contract was signed, and the company quit making it. And so we had to get a contract change to get the replacement model for that. There were no major structural changes. Once the production engineering was completed, the shipyard was not allowed to make any changes in any drawings independently. And then we discussed new business, which often was where we're going to eat, you know. But anyway, yeah. But another important and key thing was we could not adjourn until all decisions that needed to be made were made. You couldn't delay making a decision. And but like I said, we were connected 24/7 at that in 1991, 92, 1990 time frame by telephone and fax. Okay, and we did collaborate. For example, the lawyer was the contract negotiator for those OFM contracts that the design manager and the contract manager supported and were present at all the contract negotiations. I covered things about contract goals because all the contracts were negotiated, fixed price with incentives and penalties. And the contract manager was making sure that the progress test and verification of each contract had the proper items in there. So as he managed the progress and the quality of deliverables. Okay. And that's pretty much the management scheme and how it worked. And that team was, let's see, here we go. In the 5th month, and that's just a fuzzy newspaper clipping from an Italian newspaper in case you can't read it. At the 5th month is when the program was introduced into the public domain. It was the Yacht Club Costa Smeralda, which is a yacht club in Porto Sardinia, was going to put together the team that would run for the record run, and the photograph here is actually includes the 5 program managers, and we were introduced and named at the 5th month. It's about how long it took us to get from day one to where we were willing to announce to the world there was an organization. Actually, the team started working together before the 5th month, but this is the first public notice. And we're getting away from management now. I've given you an overview of the management approach. During the period from beginning in 1990, January 1990, we had my office and 2 other subcontractors had been tasked to do preliminary designs using the Allison 571 turbines to start to get different information on which is the best hull form: round bilge, hard chine, double chine. And these preliminary designs, also started providing some early serious weight estimates and things like that. But the end product of these preliminary designs was to deliver a towing tank model to Carderock. We had booked Carderock for the month of January 1990 on their high-speed carriage, and we tested 3 models in extreme sea conditions. Almost no calm water results. We were making all decisions based on seakeeping capabilities and measuring the accelerations and motions and pitch and resistance. And for the January 1990, I spent a lot of time at Carderock riding carriages and gathering daily results so that we could be doing analysis as the testing went along. And at the end of this period, in early February, we picked the hard chine hull form as the hull form that was going into the contract package. And at that time, and I missed over the point that during the fall of 1989, the Allison 571K turbines failed their endurance tests. They could not complete a 1,000-hour test on a duty cycle, and they had the redesign for a internal bearing was not well supported, and they were doing those tests. There was also 2 had been introduced, or actually put into a vessel, and the vessel was running with 2 571s, and they also encountered vibration problems. And so at that moment, while we were using the 571s to predict the power during these preliminary design tests, we switched to GE LM 1600s. And we had began working on the contract plans and specifications in the late fall '89 with the GE LM 1600 turbines, which were rated at a touch over 17,000 horsepower apiece. So during the February timeframe, we had put together a build contract, and we were using that to negotiate with shipyards. And we had some bumps in the road. Early on in '89, one of the vendors who was developing very large water jets decided not to participate after they had said they would. So that pushed us into Kamiwa water jets, which mostly we tried to have a plan B for everything because there was risk that we didn't control. And after we got to the contract plans and specification stage, the first shipyard we went to negotiate with declined to even offer to participate. And that was, getting pretty late in the game because we already had OFM contracts on gears and water jets and gas turbines. The final build contract was awarded to Fincantieri in the middle of May in 1990. I think I got that right, my memory. From the middle of May 1990, they did production engineering and construction and delivered and accepted OFM and delivered the vessel essentially on schedule. But the vessel was built inside a building, so there would be no weather delays, and also would be out of sight. It rolled out, it was pulled out of the vessel ready to go, except for dock trials and things like that. In March of 1991, it went into the water. Dock trials were run, builder's trials, and acceptance trials. And the vessel was delivered fully classed by DNV. We made a major change we worked very closely with DNV on this project. After Destriero, here's to give you an idea of the construction. This was not a lightly construction. This was built to warship type design criteria. This is one of the modules. This is in March of '91, the vessel being towed out of the construction building. And this is the other end of the vessel. And I just want to point out a couple of things. It's a big boat. How's that? And these teeny little fins, it's a little over a yard deep, were necessary, which was a result of model testing and propulsion testing and radio control model testing in Sweden to achieve controllability with one steering water jets. One of DNV's class issues was you had to have a redundant capability of steering. And with these two fins, port and starboard, had provided enough of what they provide. There are feathers on the Era. How is that? The capability that the vessel could be completely steered and controlled throughout its speed range with only one steering unit working. And there was a lot of development work on those fins in terms of radio control model test in a lake in Sweden and offshore in wind-generated waves offshore of Sweden. We were doing radio control model tests to prove that when the vessel got in the water, that the expected control capability was there. Yep.
So it steers just with those fins rotating like a rudder, or
Nope.
is there differential thrust?
No, they're fixed. They're fixed fins. That's right. It's arrows on a feather, okay? You
So
put
then
them.
it steers with differential thrust?
No, the issue was one of the issues on water jet boats is oftentimes there's virtually nothing under the water on the hull. It's a clean hull. And they can side slip in a high-speed tight turn. And these fins keep it from side slipping in a high-speed turn. But the control problem that was fixed with the fins from DNV's point of view was the vessel was uncontrollable at 15 knots with one water jet steering without those fins in a following and quartering seas. And so that's what fixed that problem.
But under your most basic, simple conditions, what is the steering mechanism?
The water jets.
Yeah, okay.
Yeah, the water jets, these steer, and then there's a bucket that comes down over the jet exhaust for braking, crash stops, or reversing.
The jets move.
This part of the jet moves.
Yeah, okay.
There's hydraulic controls. But we had to have independent hydraulic controls to give it redundancy. And that's about all I can say about management. I can tell you I know more about building it than managing it, because management turned out to be a job in itself, because there were things going on in Sweden and Norway and Germany and Cincinnati and other places all at the same time. So it was like a lot of skipping around to stay on top of these. But we the five managers rather, we did have a support people. We were not 5 individuals and nobody else was working, okay? But they were the 5 managers. They were making the decisions, and they could tell their people where to go. That's meant nicely, okay? Yes, sir.
So within your own management group, how many people were helping you? Because you went from a napkin essentially to production drawings, plus you were responsible for a test program.
During this Destriero period, there were a total of 5 employees in Donald Blunt and Associates. Me, an administrative person, and a designer draftsman, and 2 engineers, naval architects. So it's, the contracts manager only had 1 person to assist him, and it was not an employee, it was a consultant that he worked with. And he really traveled a lot because we had, 5 or 4 construction contracts, and in the R&D world, we must have had a half dozen contracts at different research facilities beside, Carter Rock. Most of our hydrodynamic testing after Carter Rock in January '90 was done in Sweden or Denmark. Carter Rock, after we finished those tests, we asked for additional time, and they said they couldn't give us any more time for 6 months. And we didn't have 6 months. Have you ever run into that? I worked at Carter Rock for 15 years, so I know the Carter Rock people. So.
Okay, so I think we can thank our speakers. So, questions?
Okay.
Is there a story behind the name?
It's, it's Italian for warhorse.
Oh.
Yes. If you look back in the Middle Ages, the knights' horses actually had armor. And the armored horses we referred to as, I think, destrier.
Thank you for your presentation. Was the contract, you said, fixed price contract?
We only had fixed price contracts.
So you delivered
And we
within the cost?
negotiated, okay.
So you delivered within the cost?
No limits to the budget.
Oh, no limit to the
Yeah.
budget. I
They were,
see.
well, they were delivered within the cost, and they had incentives and penalties, and if they delivered early, the contract price went up.
Okay.
Okay, there was a financial reward, and if they delivered a month late, there was hurtful, the price reduced.
Thanks. What is the current status of this boat? Is it still operating or decommissioned or what?
It's not operating. It still exists. It's in Germany. It's on the land. Phase 2 never took place because when we started doing the design conversion for the family yacht configuration, it was difficult to work around the machinery space in the aft end of the boat and the penetrations through the deck for the air for the gas turbines, and it essentially blocked the path of the vessel. And so from a yacht in the European style, they moor stern to. They back into the dock. And so the boarding ladders and everything are from the back end. And we would, in order to do that part, would have required either make the boat wider, reconfigure the machinery arrangements, but it became too difficult to convert it. But I will say this, the client later got a 60-knot yacht, so okay, which is operating now, okay? We actually have designed 3 major yachts that exceed 60 knots.
Yes, I was wondering, do you know of any projects either before or after this that used a similar management structure and whether they succeeded or failed?
In terms of the Atlantic Crossing record run, is that what you're talking about? No, I'm not sure I understood.
I just meant any kind of project, you talked very, unique management structure you talked about. I just
Oh.
wondered if you know if that's been used anywhere else and whether it was successful or not.
I would say no, and this is what I would say that this management approach works best when you've got a really tight schedule. You don't have the freedom to go to, like requests for proposals and negotiate, or not negotiate, but pick who had the best proposal and then go out and get contract. That takes a lot of lead time, and with a negotiated contract, you probably pay a premium in price, but you're paying maybe extra money in terms of the cost of the product in favor of guaranteed delivery. So it's a risk management approach, and I really don't think that having both have a project where you have a schedule and a budget, and the project manager won't tell you which is most important, and that's not the way to make sane and rational technical decisions in my understanding of sane and, okay, so you need a priority of either got to keep the budget and let the contract schedule grow or sink within that budget limit, or if a budget is, if your requirement is time sensitive, you're going to pay a price. But I like to say somebody in this paid the price that they got a record, which the record run was 53 knots, a little over 53 knots average between New York and England, and this longest distance in 24 hours at sea. You got that, and you got it quickly, and you got a lot of research. There's been a fair amount of this research has been published, but not all of it. And the research documentation and the analysis of the research is, I think now it's all been scanned and it's controlled by a person in England for Bravo Romeo. Bravo Romeo as a corporation still exists, and the vessel still exists. And to get it back into service, since the electronics are 30 years old, the electronics might need to be upgraded. The turbines have several improvements that GE offers for this. Turbines, the water jets are probably fine, but DNV, Det Norske Veritas, to keep it classed, it would have to go through reclassing process, and that would go by the current rule since it's been out of class for a pretty good while. We kept it in class for probably 10 years after I keep saying we. I had no financial investment in, I'm not a stockholder.
Thank you so much. I just was wondering is this one of your best I don't know, in your career? And
Yeah.
would there be anything that you would have done maybe better had you had more time or?
No, well, it's in hindsight and having matured more or less risky. I was asked a few years ago to go to Virginia Tech and lecture to the naval architect graduate students. And I was asked to lecture on lessons learned. And the lesson I presented up there was Destriero was too good, okay? It was too optimized. And what we should have done is while we met the design requirements, we should have built more flexibility in it so that changes could be incorporated without throwing away the stern of the vessel. And so lessons learned is this was a great success and over-designed, even in a shorter period of time, over-designed in a sense of optimization. Just virtually every thing in weight, structure, details. It was too good. And that's not meant to be bragging. Now, looking back at, you look into the fighter plane design history of planes, and it takes a long time to do that. And that's the Skunk Works, which gets involved in a lot of that. That's where this lessons learned came to me in reading about what they've found over the years. You need to keep some flexibility in while you're, so the vessel can operate off design if required due to some change of circumstances in the future.
Thank you. Any other questions? Go ahead.
I guess with the components, the OFM pieces,
Yeah.
you guys had to rely upon like some kind of ultra-high reliability as you were putting this thing together to maintain or to reduce complexity of, I mean, anything can happen, right? And so, you know, I know you weren't lucky, but
Yeah, we were.
yeah, you had it. Okay, all right.
Excuse me, go ahead.
But I was just curious, the approach of managing complexity, what you did to assure that this thing was really going to do it, you know, make it across and not have a failure or some crazy thing happen.
Well, just going back to the feasibility, you know, part of this, you know, the thing that started it all. Oop, wrong way. Oop, oop. This little study of coming up with these boundaries was based on 9 public domain references, and most of them were from the late 1960s and the 1970s and maybe early 80s. The hydrodynamic technology was very, very new, mature at that time. So we weren't worried about can you do it. Where the risk was getting the power and the thrust to be reliable enough to operate, you know. And the gear company was Rink Tech, now it's Rink, that designed and made the custom gears, and they had a spectacular record of successes in military ships and other things with their gears. Those were the least worry from the gear efficiency and gears, and the one concern was what would be the noise of the gears, which really would reflect forward into the yacht configuration. And it turned out that at full power, the 52,000 horsepower driving this boat, the noise and vibration, the noise levels in man spaces there were two particular man spaces. One of them had 66 dBA at full power, and this includes flow noise coming through the hull because we had treated the hull for noise, flow noise, and the other was 67 dBA. So you could talk without any assistance or Mickey Mouse ears or things. So the noise turned out to be all right. So the risk was mostly, I think, in the gas turbines because the most of the high-powered turbines have generally, in modern times, have been aeroderivative. They've been part of maybe a fighter plane, a turbine design, a jet designed for a fighter plane, and then a power turbine is added to give you a mechanical drive, source. And so it was like the Allison at that time. The Allison, they fixed their problem, but it was fixed, a year after the vessel was built, and they, had good fuel rates. The LM 1600 had really good fuel rates. They were, I don't know if you talk specific fuel consumption, but at full power, the specific fuel consumption on the LM 1600 was like 0.8 or 0.9 pounds per horsepower per hour. A diesel engine is around 0.34, 0.35 pounds per horsepower. They were getting, at full power, they were getting very close to the thermal efficiency at that time. And I suspect the biggest risk was actually the integrating of the controls and sensors. Destriero is a floating laboratory. You can't believe how many channels of data that is recorded. When it was crossing the ocean, we had every sensor was read once a minute so that the engineer could be aware, because in the software there were flags put, if it gets bigger than or less than, rings a bell. DNV at the last minute required us, let's start back to the Carderock test when we ran all these seakeeping tests. The vertical accelerations on all three hull forms were less than 1 G in Sea State 5. And DNV made us design the structure to 2 Gs, okay? And then when the vessel was getting delivered, they refused to give us a certificate of class unless we put an audible alarm for vertical acceleration on the bridge of the vessel. The audible alarm had to be set for 1.5 Gs. The audible alarm has never gone off in any sea condition the vessel has run in. So the ride quality is good, and if you're thinking seakeeping, what you need to do is think of not a Boston whaler skipping across the water, but think about the ratio of significant wave height to the cube root of the volume of displacement. If you can keep that ratio small, and small would be like 0.25, ride quality is generally acceptable. If that ratio gets a little bit bigger, then the vessel is likely to start leaping out of the water. So there's a lot of mature technology that's come out of, all of this.
Let's thank our speaker again. He's gonna be around if you have any other questions. Thank you.